I want to talk about what just happened. In the last video, I showed you how Newton's method can sometimes fail. So we went through a problem and attempted to use Newton's method to approximate a solution, and then the sequence of numbers we were getting from Newton's method was just exploding to bigger and bigger numbers that were alternating positive, negative, positive, negative. I'll show you graphically what's going on with that. Yeah, so this is the Desmos demo that I used to kind of demonstrate, explain Newton's method originally. I'll send you a link to this, and you can change this function. I'm just going to delete that function and replace it with the one that we were working with last time. The cube root, CBRT, cube root of x minus 0.4. So that was our function we were dealing with, and our initial guess was like 1, right? So let's take our x. I'll just do it over here. Our initial guess, x1, and make that equal to 1. There we go. Now, let's see what we did. So x1 is 1. Here's the point on the graph corresponding to that x value. And then there is the first tangent line. And that first tangent line has an x-intercept right over here at x2. So there's our x2. So x1, x2. That was the negative, we just got it, negative 0.8 or something. Then you make a point on the graph for that number. There's the point where x2 happening. There's the tangent line for x2, or sorry, for that point. And then there would be the next x-intercept, x3, and now it's over here. So as you can see, we're farther away. So we bounced over to the left and we bounced back over to the right. Do it again. There's the point on the graph. Make the tangent line. There it is. And that x-intercept is way over here on the left. So as you can see, what's happening is the points are moving farther and farther away. The next one is gonna it's not even on the screen now. So wherever I put my x, even if I can bring my x, I can bring my x guess closer, right? The answer I should be looking for is this x coordinate right there. That's what like Newton's method is supposed to converge on that answer. It doesn't all the time, because Newton's method is not actually a particularly good numerical method, is what we're discovering here. If you pick these numbers, even if you pick a better guess, it's still bouncing away. Okay, so there are some numbers you can pick, I think, that might work. So this here, it looks like if I pick an x value close enough, then it can approach it. So now that looks like it's actually approaching the correct x-intercept. I mean, this is very, very close. I had to zoom in pretty far, and it's getting pretty accurate. So it's very, whether or not Newton's method succeeds is very highly dependent on what your initial guess is. And if you pick an initial guess which is like too far away from correct solution, then yeah, you can get something that doesn't work at all. So here's another problem you can have with Newton's method. Let's change this to the square root of x. Let's say we want to approximate the solution to this equation. It should be 0, but whatever guess I make, because of the way this graph curves and because it's undefined for negative x values over here, as soon as you make a tangent line and find the x-intercept, that x-intercept is, no matter where you put this initial guess, that x-intercept is guaranteed to be a negative number, right? Because this is sloping upwards, and so the tangent line is guaranteed to to be like have a positive slope, and that means it's going to have a negative x-intercept. So that's just going to fail immediately. Like you can't okay, we're dealing with maybe complex numbers at this point, right? So that's another problem you can have. And then I'll tell you one more. I want to do at 1 over x minus some small number. So something like that. Here's another example where like it works sometimes. Like if I make a guess over here, my sequence of numbers 2, 3, 4, 5, they are approaching what they should be approaching, which is this x-intercept right over here at 3 1/3. So it works if I have a guess kind of in this range over here. If I have a guess over here, it seems to work. But then if I hit my guess too far away, those sequence of numbers can bounce out over here, and now suddenly my x5 is way off on the left. So if I make my x too big, poof, right about there, right? There's a value right about here where if I make my guess too big, then it doesn't work, and now it's diverging. Same thing on the left. If I go too far to the left, go past 0, I think. Oops, I forgot. Hang on a second. Go to the negative numbers. There we go. Oh, over there. Now, let's see, x1, x2, x3, x4, and x5 is, wow, way off there. So yeah, that's diverging again. So what that means is that there's this like sweep range, right? There's this range of values here between, it looks like about 0 on the left, and over on the right, what was this number? Looks like it's about 6.5 or so, like 6.6 maybe, 6 and 2/3 perhaps. There's this range of values here where if you make your initial guess, Newton's method will produce a sequence of numbers that converges on the solution to the equation. But that's the only range in which it works. That is called the interval of convergence. It is the interval upon which, if you seed your sequence with that initial guess, then it will converge to something. But anything outside of that interval is beyond the interval of convergence. That would be numbers that are going to diverge to something else. So we're not gonna in this class we're not gonna like learn how to figure out what that interval of convergence is. But you can take an entire class called like numerical analysis, which is an entire class about different types of numerical methods that are used to solve different types of problems. And in that class, you would definitely learn about how to determine like what the interval of convergence is, so that you know not only like what type of method to use, but under what circumstances it's gonna result in an answer. So there's lots of different types of numerical methods, not just Newton's method. There's tons of different types. People are developing them all the time, new numerical methods. Some of them are, you want to make them more efficient, more effective, like functional for a broader range of situations and types of problems. But yeah, it's like a big, huge field. You could take a whole class on it, multiple classes. You can get a whole PhD in this subject. So, yeah, there you go. I think that's it for this video. Still kind of getting used to Loom.